Okay, so what is an algorithm? So an algorithm, as you might know by now, is a sequence of instructions. So it's a procedure basically to solve a problem. So for a given problem, you first come up with an algorithm and you analyze its time complexity theoretically. And then if there are more than one algorithms to solve a particular problem, you analyze all the time complexities and pick the one that has the smallest time complexity, means that will run faster, and implement that algorithm. Now, in this course, in addition to these things that we did for some problems in data structures too, in this course we will do something kind of in addition. It's called proving the correctness of the algorithm. So, in the sense that once you design an algorithm, say for example, you want to design a sorting algorithm, you want to prove to someone that your algorithm does do sorting. Okay, so that's called proof of correctness, because before you really want to go ahead and implement, you should be able to convince someone, yes, it does do what it is supposed to do, before say they pay you for programming that algorithm. Okay, so as we proceed in the semester, you will see for different algorithms you will also focus on proving the correctness of those algorithms. Okay, so as a complete package, given a problem, you will design the algorithm, prove its correctness, analyze its time complexity theoretically, and then implement it and measure its actual real-time complexity, and compare it with what you observe, what you analyze theoretically, and see it shows the same trend or not. Okay, so this is kind of a complete thing that we will do in this course. Okay, so now again coming back to this definition of an algorithm, it should be unambiguous in nature, in the sense that if it is supposed to sort, it is supposed to sort, and also for a given input, you should a particular algorithm should give the same output. So the output should not change for the same input each time you run the program. Every time you run the program for a given input, you should get the same output. That's why we mean by unambiguous. Now, for the particular problem, there may be more than one ways you can solve the problem. So accordingly, you can have more than one algorithm for the same problem. And in this course, we'll do that. And we'll design algorithms, we'll design strategies, and analyze the time complexity and all those stuff. So the time complexity, you may know by now, is represented, the theoretical time complexity is represented as a function of the input size. Typically the input is like an array or a list of integers of size n, or number of integers, or it could be also a graph with vertices and edges. Now if the input is just one element, say for example for the problem of finding whether an integer is prime or not, you don't have an array of integers, you just have one integer, and the input size is represented as log n to the base 2. So this is a computer science class, for logarithm we will always use the base 2. Okay. Now space complexity, we saw this in data structures too. So what I mean by space complexity is how much additional space does the algorithm need in order to execute, in addition to the space that you allocate for input and output, because the space you allocate for input and output are necessary, you cannot avoid that. So in addition to that, how much space you need for executing the algorithm. So if the space requirement of an algorithm does not increase with increase in input size, so it remains the same for all input size, then the algorithms have to be in place. So for example, if you have a sorting algorithm that uses say 3 temporary variables to sort an array of any size, that additional space it needs does not grow with input size. So to sort say 10 integers, it requires 3 additional variables. To sort 1 million integers, it still requires 3 additional temporary variables. Then its memory requirement does not grow with input size, so it is said to be in place. and they are also called constant space complexity algorithms. So we indicate that with the theta of 1 notation. Now we look at asymptotic notations in detail in this course. Okay. So when it comes to measuring the time complexity or analyzing the time complexity, so when you write a program or you're an algorithm pseudocode, you do several things. But what we focus on is the basic operation, the operation that takes the most time. So the basic operation is the most time consuming step of an algorithm that is typically done repeatedly. Okay. So for different problems, you could have different basic operations, and we saw some of this earlier also. So we'll kind of go through as a review quickly, and then we'll start looking at specific cases. So for example, if you're searching the sequential search problem, typically you do comparison as a basic operation. For multiplication, the multiplication operation itself is a basic operation. To check if an integer is prime or not, division is a basic operation. For graph problems, traversing a vertex and its associated edges is a basic operation. So we saw most of it in the data structures. We'll look at some of them in this module and as we go through the other modules too. Okay, so why we want to focus on time complexity as a function of input size. So if the input size is n, we get the theoretical time complexity, as we'll look at some algorithms later in this module, as a function of n. So it could be like n square or n log n or simply log n, 2 to the power n, and so on. So in this chart, I indicate the different polynomials in the increasing order of their value. So for example, if you have n values as 10, 10 square, 10 cube up to say 1 million, then log n is these numbers. Then we can see the log n values are much smaller than n. So that means, to make sure I'm recording, yeah. So that means log n grows much slower than n. Okay. So log n is a very preferred time complexity for algorithms because it is much smaller compared to n. So these are the n values again. Then n log n, so log n is less than n, and n will be less than n log n because I kind of multiplying n with log n. So n will be less than n log n, as you can see from the numbers. Then n log n will be less than n square because we know log n is less than n. So n multiplied by something less than n will be less than n square. So again you can see 10 square is 10 square, 10 square square is 10 to the power 4, and so on, and n log n values are less than n square values. Then n square multiplied by n is n cube. So n square is going to be less than n cube, and so on. So all these things for polynomial functions means what a polynomial means is the variable, which is n, is not in the exponent, is in the base. So log n is like n to the power 1, and so on. So the exponent, which is like n squared, the 2 is an exponent, n cube, the 3 is exponent. So these are constant numbers. Okay, this is not a variable. 2 is not a variable, it's a constant. So as long as the exponent doesn't have variable, that's a polynomial function like this. Whereas if you have 2 to the power n, here the exponent is n, the variable. So it's called exponential function. Similarly, n factorial is also kind of having an exponential growth, and it's even faster than 2 to the power n. So these are not preferred time complexities. So as you design the algorithm and you will find out what is the time complexity of an algorithm, it's preferable to design an algorithm to have polynomial time complexity, not an exponential time complexity or factorial time complexity. Okay. So let us look at a simple case. We should have looked at it in the previous semester also, but this is kind of setting up the stage, kind of motivating example. So I think this should be indented. Okay, so this is the sequential search problem. think I don't have an array, but let me quickly type an array here. Okay, so what we are having here is an array of integers, say of 7 integers, and we want to do a search. We want to search for a specific key called the search key k. So what we'll do is it's a simple brute force approach of going through the array starting from index 0 until we find the index with the search key. If it is there, we will stop the search there and return the search key is there. Otherwise, we go to compare with every index in the array until it's the last index. So this is like a description of the algorithm that I just explained, the brute force approach. So this is what you should be able to do. Given a problem, you should come up with a logic and be able to verbally describe it. Okay, and then once you do that, you pretty much get an idea of how to present it as a pseudo code. Okay, and so that's what I'm going to do now. So given a search key and array as input from index 0 to n minus 1, you basically write a for loop, and this is the way you write a for loop in a pseudo code. Again, there's no particular syntax. You can do it a little differently if you want to, but this is what will follow as a convention in this course. So for the keyword I equals 0 to n minus 1, and then do means you do whatever you want to do inside the loop. Again, this is not any specific language. You cannot type it as a C++ code and compile. This is just a pseudo code. Okay. So I is the loop index. So we go inside the loop and check if the element at index I is equal to the search key k. So this is equal to the comparison operation. And if they're equal, then you can stop and say return the key is found. Return means you exit from the program basically. So in this case, you are breaking from the loop and telling that you have found the search key. And if the element at index I is not your search key, you just move to the next index and so on. So if you manage to come out of the for loop and the control is somewhere outside after the for loop, that means you have not found the key. So this is like a proof of correctness, because if your search key was found in the array, you would exit from the program from within the loop. So the only time you will be coming out of the loop and executing something after the loop is if you have not found the search key. Okay, so if you have not found the search key, you can say the key is not found. So anyway, you are returning the control from the program, but you are returning it after the for loop, and that's the only place to return the control if the search key is not there. If you return the control from within the loop, it means search key is there. So this is how you could argue for the proof of correctness. Okay, any questions? Right. Okay, so when you look at the basic operation here, the comparison is the basic operation. So again, to find out the basic operation, see if there is something that is done repeatedly. In this pseudocode, yes, you are doing the iteration, the for loop repeatedly. And inside the for loop, what you do is the comparison operation that is repeatedly done for each array index. So that's the basic operation. So now we need to determine how many times we do the basic operation. So if you look at this problem, the processes to check if the search key is there in a specific at some index. So you start from index 0 and proceed until you find the search key. So if the search key is 9, then you would have to compare 9 with 5, they are not the same, so move on to the next index. 9 with 8, they are not the same, move on to the next index. 9 with 9, they are the same. So you stop the search there and return that the search key 9 is found at index 2. If your search key is 10, you go from 0, 1, 2, 3, 4 up to index 4 and return from there. So that means the number of comparisons you do depends on what your search key is. If your search key is fine, you just do one comparison and tell that you have found a search key at index 0. If your search key is like if search key is value 2, then you have to go through the entire array basically and return the control after you find search key at the last index 6. So that means at best you need one comparison if the search key happens to be at index 0. At the worst case, you return control from the program. If the search key is at the end of the array, you would have to do all the n comparisons with each index. And the worst case could also happen if the element you are searching for is not there. So for example, you are searching for element 4, the search key is 4, 4 is not anywhere in the array, so you would have to still go through the entire array using this for loop and then say the search key is not there. So in both cases, you are searching for something that's the last element in the array, or if you are searching for something that is not in the array, you would require n comparisons. Okay, so any question with this until now? Let me save this as a video.